Welcome to a lesson with Dr. Powell. Let's take a look at an incidence matrix on a digraph. This is an example. So what we're doing is we're having a map or a function that preserves Z-module structure from Z5 to Z3. Z5 represents edges. So we've labeled our edges. Our edges represent standard basis elements in Z5. Our vertices represent standard basis elements in Z3. Now, we're trying to answer the question, given a collection of edges, what kind of incidence that causes at each vertex? Namely, at each vertex, what's the flow? Net flow. Is it accumulating into, or is it going to be zero when coming in and out? Or is it going away only? And so it's going to be negative. We're going to answer that question. So we're going to first answer that question for each standard basis element. And it actually is already represented right here in the matrix that we have written. The image of E1 that answers this question for incidence. Let's look at E1. E1 goes from V3 to V1. Notice it comes out of V3, one arrow coming out, so that'll give a -1 incidence on V3. For V1, it'll give a +1 incidence. So it's kind of like a boundary type thing. So the image of E1 literally is V1 minus V3. V1 right here, -V3 right here, kind of like a boundary. Likewise, f of E2, look at E2. So we're going to have a -1 on V1 and a +1 on V2. And we could go through each one. Notice this one has zeros. That's because the net incidence here at V2 is just, and all of them are zeros accounted for if just looking at the edge E4. And likewise, for E5, we get -1 and 1. So what if we were to take a collection of vertices, such as E1, E2, or edges, sorry, a collection of edges, such as E1, E2, E3. Okay, and look at the subgraph of this that's drawn only with those edges right there. Okay, so that would be something like this. E1, and then we go right here, E2, E3, like that. Okay. So we're going to look at the net incidence caused by just these on the vertices. Okay, let's look at the vertex 3. Vertex 3, net incidence of -1. Vertex 1, net incidence of actually -1, an outflow here, because this is 0 here, and then so -1 on vertex 1. And vertex 2, you have 2 coming in, it's accumulating, so 2. Okay. Notice that for every single tip, there's a tail, which means it should be no surprise that if you add these up, you just get 0. Now, let's see how this would work with the matrix multiplication to verify how we answer our question. So let's take the collection E1, E2, E3 and write them down as follows: 1, 1, 1, 0, 0. So this is living in Z5, the domain. Right over here for edges, this represents edge 1, edge 2, edge 3, edge 4, edge 5. This represents vertices, vertex 1, vertex 2, vertex 3. So this means to add the first 3 columns together. And if we do that, -1 there, yes, 2 there, yes, we're good. The matrix multiplication worked just as planned. Now, this could have also been obtained if we thought of a different collection. Why don't we do something like E1 to E2. So let's see what happens here. 2 and 0. Notice that we should actually get so notice that here, what subgraph represents these edges? Well, you just double up. So you just draw E2 twice, but guess what? E2 and E3 are identical. And so the result should be the exact same. And is it? Well, you can try it. So yeah, double that. That's the same thing. Yep, it works just great. And so this works the same way. Another example of something that could that can happen. What if we just did E2 by itself, not doubled it up, just that? So just did E2 right here. So the subgraph we're looking for incidence with is just this. Then we would end up getting so 0 at 1. Oops, that's here 0 at 1. And V2 would have okay 1. Okay, so this looks like this. So basically, the result would be V2 minus V3. Hey, those are the ends, the final tip to the first tail. So kind of a neat idea of how we can think of incidence and the incidence matrix and map on a digraph. Thanks for watching.